All right, so our final presentation is by Wood. Go ahead.
Hi. Can you hear me?
Yes,
Okay.
we can hear you. Thank you.
Okay. Yeah, so I want to talk about a phenomenon that some may be familiar with, but others may not, that the annual average temperature on the moon and other airless bodies as well, but on the moon especially, can actually vary with depth, and it is very sensitive to the properties of the regolith, and it also has implications for the potential use of regolith to bury habitats and for thermal control. So just the basic beginning case here is if you have a constant thermal conductivity, so if it doesn't depend on temperature, then what happens is so I've got a graph here showing the variations in temperature with depth at different times of day. So you can see it goes from about 100K to 400K at the surface, but then those variations dampen out with depth and reach fairly average value. And in case of constant thermal, the temperature depth basically has the average temperature at the surface. The only exception is the effect of heat flow, which, if you go to the next slide, please, which accounts for this slight upward curve in temperature at the bottom of the plot here.
Stephen, can I ask you maybe to turn off your video? We're
If you
having
didn't
some
have any heat flow, then that being constant with depth. Skip that one and go to that one here.
Excuse me, Stephen. Stephen, are you there? Can you hear me?
Yes.
Can you turn off your video? We're having some audio problems. I think if you tried to send fewer bits, it might work better.
Okay.
That's better.
Okay. So in reality, the thermal conductivity is temperature dependent. And you can see evidence shown here from measurements on Apollo samples. So I had to move to a different room, and there's background noise, which I need to shut off. And you can see it very strongly with temperature. If you go to the next slide, please. And the typical equation that has been used in the past, whoops, went too far. There's a equation that represents the temperature dependence here. And then actually the first term here, this A term, is also temperature dependent. And you can also see in this graph that there's a hint of composition dependence. If you can see, the dashed curve is for just crushed basalt versus the Apollo actual material. There's a indication of different temperature dependence. Go to the next slide, please. So if you do include temperature-dependent conductivity, then the graph on the right shows that the average temperature profile will increase with depth within the upper 10 centimeters or so. And if you go to the next one, we can zoom in and see better what the magnitude of that increase is. So I'm just going to zoom in. Next slide, please. And one more. And you can see that the difference is around 40K, and this corresponds with what was measured in the Apollo missions, the heat flow probe as well. So if you go to the next slide. This is a plot from Hain et al. 2017 paper showing the measured and expected difference between the average temperature at the surface and the average temperature at different latitudes. If you go to the next slide. So this just points out that what I mentioned earlier about the potential dependence on composition. If you go to the next slide. So this indicates that there may be a more complicated expression for the conductivity. And if you go to the next slide, there's additional measurements from later Apollo samples where they had the material was at different porosity or different bulk density, showed that that also had a big effect on the thermal conductivity. So there's yet another variable to include. And if you go to the next slide. So something that has been needed for a while and has only been developed recently. There's been several papers in the last few years that have described a physical model for regolith thermal conductivity. This is one example from a paper I published last year, just showing the amount of detail. I'm not going to go through all this, but shows that there's a lot of factors that go into determining the conductivity of the regolith. And that one thing I want to point out here is that temperature is a factor in many of them. So the radiative heat transfer between the particles is strongly temperature dependent. That's that T cubed term that we saw earlier. And then it also, the thermal conductivity of the solid material itself is also temperature dependent. If you go to the next slide. So this is an expression for the thermal conductivity in vacuum of regolith, and it has the same form as that original expression that I showed, the A plus B times T cubed. But here we have explicit dependence on physical properties of the regolith that can be measured or inferred. So the first term here, Ks, is the solid conductivity, so that's going to be temperature dependent. And then you can see dependence on the porosity, which is the phi symbol here. And I won't go into the other factors, but we now have a way to actually calculate the thermal conductivity of the regolith. Go to the next slide. So this shows an example of the comparison of that model predictions to data. So this is from Fountain and West measurements of basalt particles in a vacuum at different densities, showing that the model does a good job of fitting the data. If you go to the next one. So using that model, you can predict what the thermal conductivity is for regolith of different composition. So here I am showing results for a basalt. There's a lot of different types and compositions of basalt, but this is sort of a just generic basalt, as well as silica glass. And you can see that especially at low temperatures, they have a very different temperature dependence. So what's going on here is basalt and most and pretty much all crystalline minerals have an intrinsic conductivity that decreases as temperature increases. And so that accounts for the trend at low temperatures. But then as you get to higher temperatures, the radiative term starts to dominate because of that T cube dependence. Whereas for glass and other amorphous materials, the intrinsic conductivity increases with temperature. And so you get a consistent increase as shown here. So if you go to the next slide. So here I'm showing an example of model calculations for basaltic regolith at a latitude of 85 degrees on the moon. And unlike what we saw earlier for equatorial regions, in this temperature range, as I've shown here on the left, the thermal conductivity decreases with temperature for basalt in this temperature range. And so that actually leads to an annual average temperature that decreases with depth. So it's actually colder in the subsurface than it is at the surface. And the magnitude of this effect will depend on, details of the composition as well as the temperature range. But this could have significant effect on the location of buried volatiles, especially in places where the subsurface temperature can actually be lower than the surface temperature. And if you go to the next slide, this just shows a similar thing, but for for a glass composition. So like in the equatorial case, thermal conductivity increases with temperature, which leads to an increase in the annual average temperature with depth. So you can see that at the same latitude, depending on the composition of the regolith, you can have very different subsurface temperatures. And I don't have a slide for this, but one of the considerations for buried habitats is that they're going to leak, and so there's going to be some water that's probably released into the regolith above, which could condense as ice, which will then change the thermal conductivity of the soil, which will then change its thermal properties, and therefore could have a significant effect on the temperature at the depth of the habitat. And so that's something that either needs to, be considered or even maybe used as a way to control the temperature of subsurface habitats. And I think that is the last slide. Go to the next one. Maybe that is the last slide. Okay, so that went quicker than I thought, but if anybody has any questions, I'd be happy to try to answer them.
Okay, thank you.